Hello everyone, this is Rohit Sharma from AITS. In this lecture we're going to review TensorFlow 2.0, introduce the APIs, and there would be 4 steps that we would majorly discuss in this lecture. Number 1, data loading and processing, and what kind of data and how do we pre-process the data so that it's ready for the consumption for the neural network. And then we build the neural network. We review some of the APIs that are used in building the network. Number 3, we review some of the model training APIs and put a network, an example network through the training. And at the end, we evaluate that model we just trained. So with that, let's just get started. And before we get started, this is the URL of the notebook that I will be sharing with you guys, so that you can take this and play around with the notebook, change some of the stuff, and continue to learn. So data loading and pre-processing, right? Neural networks, they need data sets as inputs in the form of numbers for training and inference. And a typical data set consists of either text files, images, video files, CSV data, and some of the raw data. So all this data needs to be in the form of numbers. Neural networks only take numbers. So if you have a text file with some of the words, they need to be converted into a categorical enumeration. So there would be some kind of a coding for those text or words, and the number, again, like I said, neural networks can only consume numbers. So data loading, we would go through some of the APIs. Our example we're going to take is image classification, a very simple problem of classifying handwritten digits. So we have MNIST dataset with over 60,000 images that we're going to use. We pass it to the neural network and let the network classify the images. So image files are decoded into integer values, typically between 0 to 255, using special libraries like OpenCV or framework provided APIs that does that work. And if we have tabular data like Excel spreadsheet or CSV files, these are turned into numbers. And like I said, categorical values using libraries like pandas or NumPy. So Keras actually provides a dataset APIs, and I want you guys to look at this URL. There are some popular datasets that are already available as part of TensorFlow installation, and Keras does provide those APIs. And make sure that you go through the further reading section that I've listed 2 of them. At least skim through those and see what else is there. So with that, let's get started. So our sample problem is essentially recognizing hand digits through a network. And for that purpose, we're going to use a MNIST dataset, right? So in this, our example, we would use Keras APIs that lets you instantiate an MNIST dataset object with method to shuffle, load, and split images into train and test dataset. And if you don't understand the reasoning behind some of this, don't worry, we will go and cover that again in the applied theory section. Here we are just reviewing the Python APIs from TensorFlow. So the first line, what we do here is we create an object of MNIST that is already present in tf.keras. So the way we do that is MNIST equals tf.keras.datasets.mnist. Now we have this object MNIST, and we take that object and call a method called load data. And this load data will return you 4 different objects, 4 different containers. For image train, labels train, image test, and labels test. What that means is now you have 4 different containers. First 2 are for training, the last 2 are for testing. And here we are creating a Python variable called class name, which is just 0 to 10, 0 to 9. 10 different classes of handwritten digit recognition, right? So in these 3 lines, all we have done is we have loaded the MNIST dataset into the memory. So now let's inspect our data, right? And the training set is used to train the deep learning model. So we would use those 2 variable, images train and labels train, for the training purposes only. And we will not show test data set, which are held in variable images underscore test and labels underscore test, to our training code. And the test set is used to find the model that has generalized learning on test images with similar accuracy, right? So here I'm going to run this whole notebook so that we all can see the outputs while we're talking. So training images, now we load it, and I'm in this cell we are printing what is the data type and the data set shape. So the data type is for images trained that we loaded for MNIST object, is a NumPy ND array. So we will see it's a 3D array. Each image is of 28 by 28, and it's a grayscale image. What that means is it has only one channel, and there are 60,000 images. So the data set shape tells you for training we have 60,000 images of 28 by 28 resolution. It means that we get an array of 60,000 images for training with 28 by 28 equal to 784 pixels each. And in the label, again, each image is expected to have labels, so the possible values of that is 0 to 9, and we print that by using a NumPy library, a method called unique, which looks at all the labels and finds the unique values. And as we can see, and as it was expected, the labels are between 0 to 9. So now we have looked at our training images and labels. Let's see how an example image looks like. So we are using PyPlot to plot some of these images, and we take the first image that is available in the image train variable and index 0. As we know that the index of the Python starts from 0, so the first image we are showing here, and this image has values from 0 to 255 as seen in the y-axis, right? And this is 28 by 28, so the pixels on the x-axis go from 0 to 27, and y-axis go from 0 to 27, and the 0 value is represented using this dark maroon color, and 255 is yellow color. Now this is by no means is a gray image, and not because the image is not represented as a gray image. It's just the way the default PyPlot works. By default it will show these 2 colors that we have not changed. So this is a image 5, and it shows the classification level as 5 that we printed in the image using our variable called labels train that we loaded from the MNIST dataset, right? So this was our example image, and it seems fine. So our first sanity check has been done. Now we will do some of the data processing, and generally, once the data set is loaded in the form of string, integer, or float into NumPy arrays, it's time to pre-process the data. And this generally means and generally is done to make sure that the training can be done as efficiently as possible. So for pre-processing, typically means either we are tokenizing the string data followed by token indexing, or we are normalizing or rescaling the data to small values. Um, so in this case, we are just simply normalizing because all our values are limited to 0 to 255 that we already seen. So dividing all of these values by 255 brings the number down from 0 to 255 to 0 to 1. And why do we do that? Because it helps us during the training. Can we do without normalization? Sure, we can. It would have little bit of an impact on training. Training would not be able to reach as high accuracy in the same number of iterations. So we use that knowledge that by normalizing the data set, we have a better chance to get a good model. So we normalize that, and then we plot the image again, and we see it's the same 5. At this time, the values at the y-axis have gone from 0 to 1 instead of 0 to 255. So this is what we wanted to confirm, that normalization has worked properly. So this is shown in the figure. Now it's worth mentioning that the input images are inverted in the MNIST data set that we are loading. What that means is typically black number is represented using 0 in an RGB format, and the white is 255 if it's an 8-bit image. In the MNIST data set, the way it is prepared, that smaller pixel values, the white is 0 and black is 255, so it's inverted. And so if we want to change that, we have to use different set of commands in matplot to invert the image. So this cell is actually doing that. So if we use the cmap argument as cm.binary, then it shows us the white background and the black. And if we change that to, which is the inverse, and if we change that to gray, then it changes the 0 scale to 1 and 1 to 0. And this is what it should be, the original image. So just so you guys are clear that MNIST dataset has been adapted and inversed to facilitate the training. But when you guys are using the model, make sure that the numbers are represented between 0 to 1. So there will be some pre-processing that you will have to do in the program when you're putting the model to work in the inference, right? So typically in the machine learning flow, when we are preparing the whole thing, you might want to create an end-to-end application. What that means is, if you put some of this normalization, scaling, some of the pre-processing before the network, that means it's not part of the network. And when you go and deploy this on a machine, that pre-processing has to be put in before the model. And what that means is you will have to do a little bit of an extra coding to create that application. Instead, it's a good idea to put all those all that processing in the model itself. So in Keras, it provides APIs to do pre-processing in the form of pre-processing layers. So you could vectorize the raw strings of text to text vectorization layers, feature normalization. They have provided a normalization layer, and image rescaling, cropping, and things like that, right? Again, I would like to emphasize, why do we need these pre-processing layers? Because when you have saved the model and you're inferencing that model, you're running that model into, let's say, a camera which is mounted on a building. or mounted on in a USPS facility. So the camera is taking the images which are essentially from 0 to 255, and your model is taking the values from 0 to 1, and if they don't match, your model is not going to work. So what these pre-processing layers would do is to put one layer that scales the captured values from the camera. So the camera is capturing the image is fed to model, and model will do the pre-processing. And so model can consume these raw images. And so the model is end-to-end, meaning it does not require anything extra to give you the values that are needed. So end-to-end end-to-end machine learning network is achieved using pre-processing layers. And so we have finished our data loading and pre-processing, and we're going to focus on building the neural network model. So the neural network model is a directed acyclic graph of layers. And cAInvas does provide neural network functional APIs that provide really ready-made layers to build a neural network by stacking layer on the top of each other. Now, these are very important functionality and the core of a machine learning model. So I want you guys to look at this section more carefully and go and check out some of the cAInvas APIs other than what we are using here. So to simplify this whole thing, we would be using only 3 layers, meaning flatten, dense, and dropout. And the basics of creating the neural network model, and remember, this is the most important, the core of the entire model building is your model creation, right? If you go wrong here, then you'll have to do the training all over again and stuff. So two words of caution here is, one, you need to decide what network you're going to create beforehand, like draw it on a piece of paper. Get somebody who knows what kind of network do you need for the problem you have. Here we have already decided that, and we're not going to show that reasoning in this lecture, but we will discuss that in the subsequent lectures as to how do you build a network. Once you have done that, how do you bring that knowledge, that network, to use cAInvas APIs and put it into the Python code? So this is what it is showing. So we are going to use model.sequential, which is used for feed-forward networks. And then cAInvas.layers, they provide some of these ready-made layers like convolution, maxpool, ReLU, flatten, dense, dropout, and so on and so forth. So to build models with functional APIs, you start by specifying the shape. So this is just one line, but it is filled with a lot of information. So I want you guys to focus here. cAInvas.layers.flatten. So it starts with specifying the shape. So this is the input layer. This is the first layer, which is flattening the whole thing. 28 by 28, which is a matrix, is converted into a vector. So input, you must specify the input shape for the first layer, and then it can infer for the next layers, right? So the first layer goes into second, second goes to third, third goes to fourth. So these are some of the assumptions that models.sequential has made. You need to be aware that first layer would require the input shape, and rest of them are not necessary. It can infer the input shape from the first to second, second to third, and so on. So in the first one, which we are saying we're going to flatten the matrix to a vector, one-dimensional vector. So we are saying input shape is 28 by 28, and optional name is flat_1. And the second one is a dense layer, which we are saying the activation of that is nn.ReLU, meaning we are saying dense, which is nothing but a matrix multiplier, essentially your basic operator of a neural network is W times X plus B, And this is what it is. So we are saying add a dense layer, which is a matrix multiplier, general matrix multiplier, and add another activation function called reloop after that. And we are looking for 100 such layers. I'm sorry, we are looking for output as 100. The 28 by 28 is converted into a vector of 784. 784 numbers go into the dense layer, and then the output of that dense layer is 100. So 784 inputs are reduced to 100 outputs, followed by reloop. So this is our second layer. The third layer is a dropout layer. Dropout is essentially you take the input numbers and you provide the same number of outputs, but some of those outputs are reduced to 0, meaning it randomly will multiply some of these numbers to 0, and that sum of that number is provided by 0.2, meaning 20% of these numbers are just dropped, they are gone from the training. And the reasoning behind that we will cover in the subsequent lectures, but it helps the model train better. It generalizes the model better. So this layer is only useful for training. And when it comes to inference, generally this layer is dropped before the model is saved or after, before it is converted to an executable. So that's that. And the third layer is dense layer. And this 100 output, which is the output of a dropout layer, is converted to 10 using matrix multiplier. And activation of this layer is a softmax. And remember, this is a last layer. So 100 inputs that come to this layer are reduced to 10, and these 10 are passed through a softmax. And those 10 are our classes, like numbers from 0 to 9. That is our class. And you get 10 numbers out of this network, and whichever has the largest probability is your class. So if an image, handwritten image of a digit is passed through this network, and network has several numbers as in the form of a vector of 10 elements, and let's say the fifth element has the highest probability of 0.9, rest of them are 0.02, 0.03, maybe 0, then we know based on this vector and something called decision boundary that anything more than 0.8 would be our number. So we decide that this number is 5 and this is your class, right? So that's the interpretation of a neural network. Now we have created that. This is another useful feature of model object that we just created is summary. It exactly tells you what is the output shape and what are the parameters. So when you say model.summary in Keras, it gives you the model name and layer by layer description of shapes and the number of parameters that's using. Number of parameters are very important because the higher the number of parameters, that means more processing, more CPU power, and more memory. Now this is a small network, does not matter much here because we only have about 79,000 parameters. And I'm going to ask you guys to reduce this to say 5,000 without losing much of an accuracy. So this can be done, and I challenge you guys to come up with a new network that the number of parameters are between 5 to 10,000 without any reflection on the accuracy. Accuracy would be around 98-99%, and we can still reduce the number of parameters. So that is left as an exercise that you can do at home. And here it's just the same model is being shown using a different API as an image, which shows you that the input layer goes to flatten, flatten goes to dense, dense is dropout, and then dense again, and that is your output. So there's another API called tf.keras.utils.plot model that you might want to use if you are you would like to see your network as a graph, and make sure that everything is the way it is expected to be, the way you designed it. So this picture would give you that confirmation. And I've left a couple of pointers here for your further reading. There are a lot of layers that you can go through and use and read some of these APIs for layers and pre-processing layers before you build a neural network model. So this was the second section where we created a network with the knowledge that our input size is 28 by 28, and we are going to get the class of that, um, of which number is it, in the form of numbers and probabilities. So now the next section is model training. Now there are only two and very important APIs in Keras. One is model.compile, the other one is model.fit, and these are needed. Fit is essentially a training, which has a built-in loop inside. It takes the argument and starts the training. And now, before you can train, you need to compile the model. Now, why do we need to compile, and what does this compile mean? Compile means that the training, the train module requires few more parameters, like optimizer. It could be a gradient descent. It could be an ADAM optimizer. I prefer ADAM generally, so I've used ADAM here. And the loss, meaning what kind of loss do you want to use to represent the error the model would experience during training. So when the training starts, it randomly initializes these weights and biases, and the image numbers are put through that network, and it will take a guess. And that guess is going to be completely off the base, and that's how it starts. But then what happens is it calculates the error at the output as to what is the error, and that error is essentially calculated using this function called sparse categorical cross entropy. If you are curious, you should Google that term more to find out what is the formula behind that and why is it important. And if you have curiosity, bring those questions to open session, and we can answer some of those. And metrics is accuracy. Essentially, you're looking in increasing the accuracy. You can choose other points like reducing the loss and stuff. So with these three, we have compiled. Now model is ready for training, and you do the training by using API called model.fit. Model.fit takes the input data set and the labels and number of epochs. So here we gave images underscore train. Remember the variable that we created in the pre-processing data step? So that's that, which has 60,000 images of 28 by 28 each, and the labels are 0 to 9, and then we are saying, okay, go through 16 epochs and do our training. So this goes through that training and gives us the training accuracy of about 98.61 with a loss of 0.04. But we are focused on accuracy, so you will see that the accuracy starts with 90 in the first epoch and then goes up to 98% in 16. And if you want higher accuracy, you can tune that number slightly higher, let's say up to 50, and you will get 99, maybe more. So at this point, our model is trained, right? We have trained the model. So the object model that we created has everything, all the weights and biases that are trained and learned, so that if you feed an image of a handwritten digit, it will give you a class. Now we're going to put this to test. So there is another that so we move to model evaluation. How do we evaluate the model, right? So Keras provides two high-level APIs on the trained model. Remember, the model must be trained before you can use this. Model.evaluate and model.predict. Model.evaluate essentially gives you the accuracy that you can print out. It runs the model through your test data set. So like in this cell, you see it gives you test loss and test accuracy as the return values of that API, and it takes training a test set images and test set levels. Remember, these images are not shown to the training part. The training has only been done on 60,000 images. Test images are not shown. So we are curious as to what the accuracy is on the images that were not shown during training, and this is good enough. It's 97.9. So our model has generalized well on the images that were not shown during training, and that's a good sign. So model evaluation gives you the accuracy and the loss on the entire test set, and model.predict will take one image and give you what is the prediction on that image. And so this section shows you we take an image from the test set. So this is example image, test images underscore test 0, and we are simply plotting this image, and then we are also looking at what is the prediction. So this is 7, as we can see, right? We plotted that image, and we're going to take the same image, example underscore image, and then we'll put through the model prediction. So example image is input, we expand the dimension so that it matches the model, and now we look at that image. Now image is 3D, 1 by 28 by 28, because this is what our model is trained on, right? So this is CHW. This is our default format for the image. The first is channel, the second is width, the third is height. And so np.expand dims actually puts this number 1. So it was a matrix of 28 by 28, and then we are adding one more dimension so that the prediction can look at that as a 3D tensor. And why is that? Because the model is expecting a 3D tensor, not a matrix. And so if you give the matrix, it's going to give you back an error. So we need np.expand dims to expand or add another dimension in front. And so this API model.predict is being used on that, and it returns a vector, essentially vector of 10 values, which are probabilities of each class from 0 to 9. So we print the prediction result here, which we are expecting to be a vector, and then we find the largest number in that vector, and that is our class, right? So we look at the output. The shape is 1 by 28 by 28 that we actually did using expand dimensions of NumPy. And the vector prediction result is this. So it has 10 numbers, 10 floating point numbers in scientific notation. And then we take the maximum of that, and this is a class 7. So this picture is prediction has been predicted to be a digit 7 using the model that we just saw, we just trained. And then we are going to have a little bit more fun with this score. This is not required. We are done at this point. We have looked at our test accuracy, and we have looked at our one sample image if the prediction is right. And here we are loading, and having fun with more images. You can increase that number, say 10, 50, or 100, and make sure that the prediction on most of these images is correct. It has to be about 97.9%. That is the expectation. So I think we have plotted um, 15 images here with their prediction, and it looks good. Now we can also look at the test accuracy again, which was 97.9. And the last part is saving the model. And saving the model in the TensorFlow format is as simple as providing it a directory. So when you say model.save, saved model directory, it will save it in the mnist model.tf, which you see here. So this particular directory would contain your files in the TensorFlow format. So this is your TensorFlow format, another directory, and a PB, which is a protocol buffer. And so this is your um, TensorFlow format that it is saved in, and you can save it in other formats which, according to your need, might be TF Lite, might be an Onyx format. So some of that code is given here. You don't have to use it, but your objective of training a model is done. Congratulations. At this point, you can save the model and pass it for the further compilation. So I'm going to stop here, go through all the material, all the references that I provided here, get an understanding of few APIs, pre-processing, data loading, and model building and your model training. And these are less than 10 APIs. And they are very powerful, high-level APIs that can give you a model of the problem of your choice. And use those, go through the reading, bring your questions to the open session. That's all. Thank you very much.